Hello, folks, and welcome back to another broadcast from the bunker. Today's hot topic, seafloor spreading. As you can see, we have a little animation over here. Crazy stuff. So, jump into the do now, and I'll see you in a minute. Okay. So number 39 here, it says the Earth has fewer impact craters than Mercury because, well, remember, same thing with the Moon. The Moon has a lot more impact craters than the Earth, and the big reason there, the Moon has no atmosphere, right? So as the meteors are coming in, there's no atmosphere to generate friction and heat to burn up that meteor, so they just hit. Same thing with Mercury. Mercury is too close to the sun. The sun's gravity is too strong. It robs, so to speak, Mercury of any atmosphere it would have. So when the meteors come into Mercury, they don't burn up at all. They just hit the surface. All right. So got to be something about that there. Certainly, if there's no atmosphere, there's much less weathering and erosion. So that's a good possibility. Subduction of crustal plates really doesn't have much to do with it. Rotational speed, not much to do with it. And it says here Earth has fewer. Well, there it is, because in the upper atmosphere, Earth, those meteors burn up. So that one, while A looked good, the best one has to do with that atmospheric scenario where their friction is generated and the meteors burn up on their way in. All right, so we got to go with choice D. For number 40, it says, compared to the distances between the planets of our solar system, the distances between the stars are usually what? Well, the next nearest star is several light years away. So within our solar system, the planets are much, much, much closer together relative than the rest of the stars in the galaxy and, of course, the universe. So, what do we have here? So the distance between the stars is generally going to be much greater. Remember, our sun, the light from our sun, takes about 6.5 minutes to reach the Earth. The next nearest star, they say, would take about 4 light years for that light to reach the Earth. So it's a big difference in distance when you're talking about stars versus the planets. Okay? All right, 41. Which statement best describes how galaxies generally move? Remember we talked about red shift and that whole Doppler effect where you hear a fire engine coming toward you and all of a sudden it passes you and the pitch of that siren changes, right? And it totally changes. Well, that effect also works with light. And they found that, the whole wavelength scenario, when things are coming toward you, the wavelength decreases, and when they're going away from you, the wavelength increases. Well, the only way to do that is if things are going away from you. So galaxies generally will move away from one another, and that's supported by the evidence of that Doppler effect, where the wavelength of light is getting stretched. It shifts toward the red, right? Red is the longer wavelength of light. I'll show you the tables on that. And that's the accepted theory as to what's going on in the universe. The table I'm talking about, the electromagnetic spectrum, it's toward the end of your reference tables. And that's right here. We'll switch that around. And there you go. If you look, red, okay, goes toward increasing wavelength. It's a longer wavelength of light, whereas if it shifted toward the blue, it's a decreasing wavelength, and that would indicate that things are coming towards you, but that's not the case at the moment. Things seem to be going away from us, and the wavelength gets increased, stretched, and that's why they call it the red shift. Okay? Okay. We're going with C on that. And 42, the greatest difference in seasons would occur on a planet that has, well, seasonal change, remember, is because of the Earth's tilt. So the greater the tilt, the more extreme the seasons become. Well, if you're looking for a greater difference in seasons, you're looking for a greater tilt. So it's not an elliptical orbit phenomenon. It's not, not that at all. Its axis of rotation is inclined. This means that its tilt, right? That's a fancy way of saying its tilt is to 45 degrees. Now that's an extreme tilt, right? Our tilt is 23.5 degrees. But if Earth were tilted at a 45-degree angle, then our summers would be a lot hotter here in Elmont, right? We'd be tilted more toward that sun in the summertime. But in the wintertime, now we'd be tilted much further away, so the winters would be much colder here in Elmont. The seasons would be more extreme. And that's what's going on here. If the axis is tilted 45 degrees, you're going to have a great difference in seasons. Okay? Oh, I'm just looking at D here. If the axis of rotation were perpendicular, what that means is no tilt at all. Okay, so if that confuses you, that means no tilt. So if there were no tilt, there'd be no seasonal change. All right, so rule out D there. Got to go with C. 45 is an extreme tilt for a planet. Okay. Any further questions on those? Just leave the comments down in the comment section below. All right, let's dive into our lesson on ocean floor spreading here. Get those subtitles going. Okay, and that gives you a little cartoon idea of what's going on here. You have magma rising from the mantle. It's driving the two oceanic crusts apart. It's called divergence. And the ocean gets bigger, and of course the continents move. And that's what we're going to chat about today. It's called seafloor spreading. I want to start with a quick little clip here. Check it out.
The Atlantic Ocean, which now divides Africa and South America, owes its very existence to this geological cataclysm that tore Pangaea apart.
The supercontinent looked like this, made up of the present-day continents of Africa, South America, India, Antarctica, and Australia. The cracking started here and split the continent into the present-day continents of South America and Africa.
In geological terms, it happened incredibly fast. The crack opened northwards at a speed of 2 inches per year, the split unzipping the land as it went along. Fountains of volcanic fire leapt through the crack. The entire process took only 5 million years to complete. Evidence of the unzipping is clear. The shorelines of South America and Africa match perfectly, and under the ocean, the mid-Atlantic ridge divides the two continents almost exactly down the middle, where it still pushes them apart.
All right, again, that's called an area of divergence. This is a great, cartoon version, if you will, showing you the features on the ocean floor. There's the mid-ocean ridge where that divergence would be occurring, and it literally splits the ocean apart, making it bigger and moving the continents away. Okay? Where does this spreading occur? Well, it occurs in the middle. We call it mid-ocean ridges. The one in the middle of the Atlantic Ocean is called the Mid-Atlantic Ridge, but it is a mid-ocean ridge. And here you can see, different pictures of what's going on there. And we're going to analyze the evidence for that. Okay? At a ridge or a rift valley, usually they call it a rift valley when it's on land, and a ridge when it's underneath the ocean. Okay? How does it happen? Well, take a look at the animation there. You got magma that wants out, right? Extreme heat and pressure wants out, and when it does, it rises up like a volcano, and that magma turns into lava, of course, when it exits, cools, hardens, and pushes the plates aside. Okay? Watch carefully. This is over time. This is a progression over time. You could see initially there was no ocean. And of course, the water would be somewhere else. But when you split the continents, you create a low area. And water goes downhill. So whenever it rains, floods, whatever, would go into that low part. And that's the birth of the ocean right there. And over millions and millions of years, it spreads wider, the ocean grows bigger, until, of course, today we have, the gigantic Atlantic Ocean. All right, mid-ocean ridge again in the center. The two ocean plates move apart, and the magma rises from the mantle and creates this massive convection process. Okay, is the Earth creating new ocean crust? Well, if the magma rises and comes out as lava, right, cools, and brand new rock, oceanic rock is basalt, so then yes, in effect, it is creating new crust. All right. This is 240 million years ago. The Atlantic Ocean was much smaller. This is only 150 million years ago. You can see as time went on, it got bigger. And this is today, right? 0 million years ago is today. And there is our expanse of Atlantic Ocean right there. All right. The colors are going to talk about the age of the rock, and we'll get into that next. Obviously, the youngest rock is when it comes out in the middle, and it gets older and older as it's pushed aside. All right. This is a beautiful map showing you the age of the rocks. If you zoom in on the bottom here, this scales in millions of years. The red, of course, is the youngest, and look at that. The youngest rock is in the center of the oceans. Is that a coincidence? No, right? Because that's where your lava is coming out, and you have brand new basalt being made. And as you go from red to yellow to green, you're going away from that ridge, and incidentally, you're also getting older and older. Okay? Where on the ocean floor are the older and younger rocks? Well, pause real quick, pencil it in. Hopefully you realize if you're coming out in the center, right, your younger rocks are going to be at A, and your older rocks by the continents at B. Okay, so label your diagram appropriately. The oldest rocks are going to be near the continents. You're also going to have the greatest number of fossils near the continents because older rock, there's been more time for creatures to live and die in those areas, and you get a lot more layers of sedimentary rock piled up because this rock is many, many millions of years old. Okay? Okay. Another quick little clip for you. This is going to tie in an idea of magnetic reversals. See if you can follow that. We'll talk about it afterwards. But over time, the Earth's magnetic poles have changed, and that's recorded on the ocean floor. Check it out.
If the continental drift theory leaves you scratching your head, you're not alone. Scientists had a problem with it too, because they just couldn't imagine the continents plowing through solid ocean floor on their way to wherever they were going. Then, during the 50s and 60s, new techniques and instruments, like sonar, began to provide some answers about the constantly changing landscape of the ocean floor. One thing scientists found is that continents don't actually plow through the ocean floor, but how the continents do move proved to be even stranger. New mapping techniques revealed that the ocean floor is home to the largest mountain chain in the world, the mid-ocean ridges. Divided in half by a deep rift valley, the volcanic mountains of the mid-ocean ridges are one of the 3 zones of earthquake and volcano activity on Earth. As lava pushes up through the Rift Valley, the ocean floor on either side of the Rift Valley is pushed away. As the lava hardens, new ocean floor is formed in a process called ocean floor spreading. Ocean floor spreading explains how continents drift. As the ocean floor moves away from the Rift Valley, it takes its continent, if it has one, with it. Samples from deep-sea drilling machines showed that rocks next to mid-ocean ridge are younger than rocks farther away. So as the ocean floor spreads, the older rocks are moved farther away from the ridge. Which color represents the oldest ocean floor?
So what do you got? Which is the oldest? That would be furthest from the middle, right? Hopefully you said your blues.
Scientists found more evidence of ocean floor spreading when special instruments were developed that could detect magnetic stripes in the ocean floor. These invisible stripes formed when the magnetic minerals in lava lined up in the direction of the Earth's magnetic poles. They provide a permanent record of the history of the Earth's magnetism. What scientists learned is that the Earth's magnetic poles have reversed themselves 9 times in the past 3.5 million years, and each reversal is conveniently preserved and recorded by a magnetic stripe. How might the pattern of magnetic stripes support ocean floor spreading?
Well, if you take a look, it's totally symmetrical, right? You got south-south, north-north, south-south, so that symmetry must have started in the center.
The pattern of these magnetic stripes is identical on both sides of a mid-ocean ridge. So as magma hardens into rock, half moves in one direction and half in the other. Clear evidence of ocean floor spreading. So if new ocean floor is being created and the old floor is spreading, the Earth must be getting larger, right? Using radioactive dating, scientists have determined that the oldest rocks on land are almost 4 billion years old, but the oldest rocks on the ocean floor are only 200 million years old. This suggests that the ocean floor is being destroyed as fast as it's being formed. But how?
So ocean rock is denser, right? Basalt is denser than granite, and they're going to talk about it subducts. It goes back down into the earth and gets destroyed. Why?
The answer lies in the deepest parts of the ocean. Long, narrow, V-shaped crevices called trenches. Found along the edges of the ocean floor, near continents or groups of islands, trenches can be over 11,000 meters deep. Many of the deepest trenches are found around the Pacific Ocean. As older ocean floor is pushed away from mid-ocean ridges by new ocean floor, it eventually subducts or slides deep down into the Earth along the trenches. This leaves the size of the Earth's surface the same. The subducted ocean plate is melted by the heat in the mantle. It can then be recycled into new ocean crust at the mid-ocean ridges or rise through the crust to form volcanoes. And now that you understand how ocean floor spreading causes continental drift, there's nothing left to do but hang on and enjoy the ride.
Pretty cool stuff, right? All right, hopefully you followed that. As far as that magnetic orientation, a compass points north, right? Everybody hears, oh, the compass always points north. Technically, it's not always true north, right? The compass points where it's magnetically pulled. And in different parts of the Earth's crust, you have different amounts of iron, so sometimes the compass can be a little bit off. But in general, currently it points north, but it wasn't always that way, right? In the past, it would have pointed south, and then before then it would have pointed north because the Earth's poles have switched over time, and all of this has been recorded in the ocean floor. If you remember, basalt is a mafic rock. And mafic rocks have a magnetic mineral in them called iron. And iron is going to turn, where it's attracted to, just like the compass. And that's what these black and white stripes are showing you. They're showing you magnetic reversals where the iron was pointing north and then south and then north because of the Earth's magnetic field having changed over time. All right? They're symmetrical patterns. They're magnetic lines. They call them stripes sometimes. They're not. You can't literally see black and white on the ocean floor. That's just a symbol of which way the magnetic field was pulling. All right, and they are symmetrical on both sides. Okay, normal polarity, what we call normal, means that the compass points north. Reversed means the compass points south. Remember, the compass is going to point wherever the magnetic field, dictates it, and of course that has seemed to have reversed over time. Okay. So here we get older and older. Now they're red and yellow stripings. But that's just showing you, again, what that black and white is showing you, the reversals. Okay? How do we determine this pattern of reversals? Well, watch the simulation here, right? Whenever you see those symmetrical colors on opposite sides of the ridge, there must have been some kind of a switch. So in this diagram here, if this one is north, then this one must be... very good, north as well. What about 2? Right, it's next to a north. It's got to be the same as this one, though, because that's the symmetrical partner, if you will. So that's going to be a south. And you keep going. This one would match up to this one, so that's got to be a north. And finally, 4 would match up to the other opposite shore here, and that would also have to be a south. right? And those are magnetic stripes, if you will. They seem to alternate every couple 100,000 years, and they say we're on the brink of a switch pretty soon. The interesting thing is that you don't find the same fossils as you go out. It's almost like they disappeared. Some kind of a mass extinction seems to have happened at the same time as these switches. Humans were never around for a magnetic reversal, so it'll be interesting. I don't think we're going to go extinct from that. But, life, certain life, as far as migrating and finding food and that relies more heavily on the magnetic field, and maybe that caused them to go extinct, right? It's one of those theories. You could argue that humans rely on our magnetic field big time nowadays with our technology, right? Our cell phones. So could we go extinct without cell phones if this whole magnetic reversal screwed them up? Food for thought, folks. But I digress. All right, so let's try to wrap it up. There are 2 diagrams in your notes here. Follow the directions here and see if you can figure it out. All right, pause, try to figure it out on your own. Here we go. These are the 4 you have to pick from. Which one of these 4 would fit here? Right, so you go through your 4, you match up. Well, let's see. I have a black here. There's got to be a black there. I got a skinny white. There's got to be a skinny white there. And hopefully you chose which one? Well, hopefully it looks like that. Okay, notice it's totally symmetrical, and that would have been choice 2. Okay, the thickness will tell you how many years it was of that certain polarity, and of course the distance out can also be determined. All right, on this one it asked you to do a couple different things. Which rocks are more or less dense? Remember, basalt is more dense than granite. Basalt is going to be in the oceans, granite, of course, on the continents. So hopefully you picked for more dense your oceanic rock, your basalt, and for less dense you chose your continental rocks, your granite, your A and D. Here is age versus location. Well, as you go from C to B, what happens to the age of the rock? Well, the youngest rock is coming out here, and as you get toward the continent, it's getting older. So from B to C, now you're going toward the ridge, it's getting younger. Hopefully your graph looks something like that, getting younger as you go from B to C. Okay? A couple of summary questions. Which diagram makes the most sense? If this is an ocean ridge, it's diverging, so you got to have convergence looking like this. Hopefully you chose diagram 4 there. The occurrence of high heat floors at the ridge center provides evidence of, well, if it's high heat, there's probably some kind of magma coming out there, right? The convection of magma in the mantle. With this one, we just did a similar thing. You had to figure out the magnetic striping there. As distance from the center of the ridge increases, the age. So if you get further from the ridge, what happens to the age? Well, hopefully you said it's getting older, which means the age must be increasing. Okay? All right. Any further questions? You know what to do, folks. Put them in the comment section or shoot me a question on Remind. All right? Enjoy the rest of your day.